Hey guys, I'm Jose and welcome to this new tutorial of the Plethora Library in processing. I think that in the last tutorial we saw how to just create a series of agents and they would be wandering around. So if you look at the examples and you go into Plethora Library, I mean, I'm assuming that you have installed already the library. So if you go here to library, right, download the library and install it. Right, we will also be looking at the reference file here and how to just understand some of the functions in this session, right? So I'm going to open that, and we're still going to be looking at the Plethora agent. So you see some of the methods that are ready for to use here. So let's use some of that. If we look at some of the examples, we probably were looking at something like draw a trail. Something similar to this one, right? I have just kind of increased the size of the font as well, so you can actually see better. So this is an example, for instance, that similar to the one we did, but it's in 3D, and basically agents start flocking around, and they're drawing these lines, right? So these lines. So that's in the examples already. Let's see how to just implement something like that, but also like look closer to functions like flock and how do they mix with some other kind of functionality. So I'm going to start from scratch, just not to leave anybody behind. And I'm going to start by importing toxi.geom because, as I've said before, the Plethora library, it's a dependency on depends on toxiclibs, right? So I'm going to also bring plethora.core and import PC. So these are kind of the libraries that I'm going to be using. So if you don't have any of those, just go and download them because we will need them, right? If you're not sure about how to download libraries and bring them in, just go to tutorial number 10 on the processing series and it will show you everything about these kind of libraries, and we've been using PCCam for a while and toxiclibs as well, so I'm gonna assume that you know how to do that. So let's do a window like so. Let's see if we're having any errors. No, we are not. So background, black background, and let's do an instance of PCCam. Right, so that's the camera, and camera equals new PCCam. So we have the new camera, and in order to see something in the scene, we're going to do a box of 600 units. We're going to do stroke black. We're going to change this guy to stroke maybe 235. And no fill. Right? So very straightforward, just like a 3D setup for to work with PCCam and a 3D environment, right? So we could do the window slightly bigger, so 900 by 600. I'm not gonna save this for now, doesn't matter. So there we go, we have a decently sized window and a 3D environment to work. So let's start bringing some of the elements of the Plethora library. So we're gonna do an array list of agents. So we're gonna call these we were calling it Bob before, but we could call it like okay, let's call it many Bobs still. So many okay, there we go. Many Bobs, right? Or you could call it voids if you want. That's kind of the classic definition of agents. So we're gonna call it many agents, right? That's good. And we're gonna do many agents equals a new array list, right? So basically what we need to do now is create a series of agents. So we're going to do that in a for loop for integer I equals 0, I smaller than, we could say 100 for now, I plus plus, right? And here in this, inside this for loop, we are going to just create vec3d, like v, doesn't matter, or origin. So this is going to be the origin point. That is going to be a new vec3d in the coordinate 0, 0, 0, right? I mean, you could just specify nothing in the vector and it would be 0, 0, 0, right? So, but that's fine. Plethora underscore agent. We're gonna call this guy pop as usual, equals a new plethora underscore agent, and this needs this, so the instance of the processing sketch as we explained in the last video, and the vector, right? So origin. So there we go. We have our agents. I am gonna save it just in case we missed something. So I'm gonna call these Plethora tutorial 02. Right, so there we go. Let's see if we're having any errors. Still no errors, but nothing happening in the screen. So, and we also need to add this Bob guy. So many agents. So the list dot add Bob. So now we have 100 entities inside the array list, right? So we could do this create 100 or so many agents in the array, right? So if we want this variable to be something like integer pop equals 100, we could use pop here, right? As we've said before, I mean, there's different ways of dealing with array lists, but like for now we're gonna keep it like this. So I'm gonna press Ctrl T just to make my code a bit simpler. And now we basically need to just do a for loop to call some of the functions, right? So I'm gonna just copy this guy here, and the only thing I'm gonna change is instead of saying pop, I'm gonna say many agents dot size, meaning that loop through as many agents we have in the list, and make sure that you kind of close the parentheses here. So we are going to make this line that says plethora agent Bob is from the type plethora underscore agent, many Bobs dot get, or many agents dot get I, and then we can here we could start calling some of the functions of the library, right? So here we could say bob dot display point, right? And the functions that of the library, we could just start looking them here, and we could see that we have display point that will display the point location of the agent, right? So that's a very straightforward one, just to kind of be able to see them. And we're going to do a stroke color 255.0.0, right? So right now we should only see, let's say, one agent in the middle of the screen because they're all in the same place, right? So there we go, we see it. It's actually there. But so we could randomize this a little bit. But instead of randomizing, we could just start adding some of the some behavior to this agent, right? So we could say bob dot update. So that would actually make him update its position if it had any information of what to search for, right? So it doesn't right now. So we're gonna just have to add some information to search. So let's create a little bit of a randomness in the origin. So random minus 100, 100. So that in X and in Y we could say. And you see that now we should see our 100 agents flat in the screen, right? So let's make them first start looking at seek. So Bob dot seek, and seek, if you look into the library, and if you look at Daniel Schiffman's or Craig Reynolds' steering behaviors, seek. Where do we have seek? Seek, here we go. It requires a vector, so you could determine any point in space and a factor of so how strong are you going to seek that vector, right? So let's do something like we need to provide a vector, so target, and maybe just one for now, but we don't have that target specified, so specify the target. It's going to be vector 3D target, and let's make it equals new vector 3D. So 0, 0, 200, right? So just a point in space up there. And let's see what we get. And you see that all the agents are kind of looking like seeking this point in space, so on some point here, and they are basically trying to grab it, and then they pass because they have this kind of velocity, and they pass to the other side and they go back, right? So they are kind of just going to that point and then going back, right? So that's very straightforward. That's the difference between the function seek, and this is very kind of following exactly like Craig Reynolds behaviors, different to the function arrive that we could just do here. I think that's, let's see, oh, do we have function arrive? Yeah, that doesn't have a factor. So function arrive is the same as seek, but doesn't have a factor in it, and in a way factor arrive should kind of slow down towards the point, and so in a way it's slowing down to actually get to that point, and then you will get there, right? So for now we're gonna just give seek. So that's kind of handy. Let's look at some other kind of better ways of visualizing these agents, right? So one of the ways in which I kind of been using agents in the past, it's actually showing their past position in terms of the tail, not a trail. I mean, you could draw the lines, and we will end up doing that as well. Again, because it's like a lot of people have told me they're interested in just how to draw lines with agents. So first, but we're going to see the tail function. So let's look for draw tail points, and you see that draw tail points is one of the few functions that I did for the library that actually uses color information, because I wanted you to be able to specify the initial color and the end color of the tail. So it's RGB alpha size, RGB alpha size, right? So let's copy this line, and then let's say Bob dot display tail points, right? So the values that we have to specify is RGB alpha size. So RGB, so we're gonna say 0, 0, 0 RGB, that's 0. Alpha 255, and size we're gonna see, let's say maybe 3, right? And then we need again RGB alpha size 1, right? But this won't work unless we initialize the tail, right? Because the tail, it's an array that lives inside the agent, right? But by default it's not, it hasn't been initialized, right? So what you need to do is at the beginning of, in the setup, just say init tail, right? So, and you determine how big you want this array to be, right? So you could say here bob.init tail, and you will say maybe 20 points, right? So that will actually make every agent have a tail of 20 units, meaning 20 points of their past location. So let's see if this works. So now we have these guys here, and we are not getting them to update, right? So that's because we also need something called we need to update the tail. So let's look at one of the examples here. So for instance, we have one of the examples that should show us the use of the tail, and or any of them really, like flocking actually uses the tail already. So we're initializing the tail, and then we have update tail. That's the function that I was looking for. So here we're gonna say bob.update tail, right? And it's funny that I didn't find it here. Oh, here it is. Yeah, and the rate is like, do we want to update the tail every frame or every other frame? And why did I did this separately from the update function? Is because maybe you don't want to have a really long tail. Let's look at what the update tail does. You see that you have this kind of situation where you have the size of the spheres going like that. But the length of the tail determines, it's based on the speed of the agent, right? So actually in this case we gonna have, this is the beginning and this is the end. So we could say that, and you could say this is 0. So they're kind of disappearing like that. Yeah. But the length, if you actually determine that you want to update every other frame, you could get that the tail is a bit more scattered, right? So if you put something like, I mean, obviously you will start kind of just scattering it quite a bit if you put something like 10. But you see that it's almost like a ghost effect of every 10 frames it kind of recalculates the tail position, which is the ghost position of the agent, right? So maybe that's what you're looking for, and it serves the purpose. For now, I'm going to just leave it in something like 1, and just going to make something a bit more subtle than what we had before. So something like this, right? So you can see that we can see better the velocity of the agents as under past position with this idea, right? So we have update tail and display tail points. What else can we do here? We can start kind of bringing some behavioral functions, right? In this example of flock, for instance, we actually are using the function flock, and this is the one that I want to talk about right now. So we're gonna do seek, and then so this is gonna be our display functions. Right, and then we have our behavior functions, and then we have our update functions. Right, so let's add here a line for flocking. So bob.flock. And here what we have to specify is, because flock is a calculation of not only the agent itself, but also its neighbors, or like basically agents that are around him. So you need to specify something like what is the collection, right? So in this sense, the collection or the array list here, it's many agents, right? So that's the first value that you have to specify for flock. And then you have to specify a series of values, right? So you have to specify 6 values. And the values are the following: cohesion radius, alignment radius and separation radius, cohesion scale, alignment scale, and separation scale, right? So what does this mean? Like flocking is a behavior that it's composed out of 3 internal behaviors, one of them being cohesion. So you have to determine which is the radius in which agents are going to be attracted to other agents. So I'm gonna put 80, right? Um, what is the radius in which agents want to align to other agents? Alignment, it's gonna allow agents to kind of like follow the similar direction that agents in a specific radius. So right, we're gonna do 50. And then what is the radius in which agents don't want to collide with each other, right? So what is the internal kind of space of them? So we could do something like 30, smaller one. And that's the first three values, the three radiuses of cohesion, alignment, and separation. And then you have to specify three more values. And it's like, how are these forces of cohesion, alignment, and separation kind of scaled, or how strong are each one of them compared to each other force, right? So if you put 0, 0, 0, that's just basically saying nothing. There's no force. If you put 1, you're saying there's a factor of 1 for cohesion, but there's nothing for alignment and nothing for separation. So you can just use basically cohesion, right? By putting 1, 0, 0, right? Or just alignment, putting 0, 1, 0, or just separation, just by using 0, 0, 1. So we could actually try this one and see what we would get of this flocking function only by putting a bit of separation. So we still have the seek active, so we're still doing whatever we were doing, and now we will add a bit of separation value to the agents, right? So you see that they start going to target, but they are trying to stay away from each other. When they get close to the target, they have to renegotiate their own kind of distance between each other, right? So that's kind of the solution, if you want. Like, they are kind of trying to get as close as they can to the target, but they don't want to collide with each other, right? So if you make this force stronger, like 4, you see that at the beginning you have a much stronger separation, and you see that they definitely want to be there, but they cannot really collide or get into the space of the other one. So you get this kind of nice swarmy behavior. And in this case, we're just using separation, right? And we're using separation and also follow target with seek. So you could start really kind of just with these two functions, with seek and like putting targets in space, or just with flocking, you could start combining and getting quite really good results, right? Like, you could actually draw with agents by placing one target, and if you kind of get close to that, maybe switch to another target and then another one, and you could start basically kind of determining how you want these agents to kind of draw something, right? So let's look at what happens if we start bringing. So I'm gonna leave just separation quite strong, like 2, but maybe a little bit of alignment, right? So you could say 0.5 here in alignment, and you could start. It's really up to you really to start testing of how these behaviors are different now, because you're adding a little bit of alignment, and then the behavior starts kind of changing in its quality, right? And you see that they kind of move a little bit more together than before. And again, if you do cohesion, you're gonna make sure. In this case, we don't need cohesion because in a way the seeking is providing a cohesion effect, but you could also start testing if you remove the seek and start adding cohesion in, what happens, right? I'm gonna add to this the idea that before we were actually printing the lines, right? So let's look at the example of draw trail. And if you remember what we were doing last tutorial, so we are looking at a function that it's called drop trail point, right? So drop trail point, which is something that we want to do, is just gonna, and in our case it's called Bob, right? Drop trail point, we're gonna say a maximum point number of points that an agent can create. It's 800. That's a lot, actually. You could say 300. And there's a threshold of distance for them to be connected. And then you have to also do a draw trail, right? So we are gonna just here in the drawing, well, I'm gonna put this down here. So we're gonna say Bob dot draw trail, and now here this is the value that it's actually the threshold for lines to be connected, right? This is saying drop them every a maximum number of 300 trail points, and drop them every 5 frames, right? And we could determine the graphics of that, just to make sure that we're getting kind of a stroke that has nice thickness and graphics to it. So let's see what we're getting now, right? So you see that the agents are doing whatever they were doing before, and they're drawing in 3D space now. If you start really playing with this, I mean, it doesn't need to be inside this box. I mean, this box now doesn't really mean anything, but maybe you want this vector to be somewhere in 600, right? And you want a bit less alignment, and you could start really playing on how these values create a different configuration. So you see that this point is kind of somewhere higher now, and they kind of created this threaded network. And if you really play with the number of agents, you could say 600 agents. You can see that we could start creating something a bit more fibrous like that. And they are kind of just starting from one point, getting to another point, and drawing their position, and in a way kind of obviously negotiating of how to get there. I'm going to finish this tutorial that it's already kind of a bit long, but by just showing what if we want to, let's say, export this drawing into Rhino, right? So I'm going to just there's one example here in processing already that it's really useful, that it's a Dxf Export, right? So I mean, this is not the best way of exporting, but it's good enough. And you can just go through this example and see it, and it's really straightforward, it's really short, and it should work fine for our purpose. And I'm gonna see if this works, make sure that it does, right? So we're gonna start by importing, sorry, this sometimes happens to me. We're gonna import this library that it's a processing.dxf, right? So this library would allow us to kind of print the geometry that we're creating into a DXF file, right? And we need to make sure that we have our script here, and we'll see where that file is going to be created. And we're also going to start this script by just saying boolean record equals false, right? And this is going to be a variable that we're going to just switch on once we press a key like R to record the data, and then we're going to record all the data into the DXF file, and then basically stop recording once we are done, right? So that's the first thing we need, is a boolean. It's an true or false value. If you go all the way down here, just after the draw, we can actually draw the function, like write the function. So void key pressed, right? So if we press a key, which key? If key equals R, right? And that means that if I press R, but I also, if caps on, it's on, we could just do an additional, we could say or key equals capital R, right? So if either case, you execute this line of code. And what is this line of code? It's just record equals true, right? So if you press R, you're gonna start recording mode, right? That's our own variable to kind of start recording, right? So that's simple. So what happens when we start recording? Here we are gonna, actually I'm gonna just put it after the box, because if, well, we'll put it before the box, and we'll see that we can actually export the box as well. But once we're gonna say if record equals true, right? This statement is kind of redundant, right? If you just put if record, we will assume that it's asking the variable record that is a boolean if it's true, right? But if you want to just be explicit, if record is true, what happens? And here I'm just going to copy this line of code, which is the magic of the recording, right? So begin raw in a Dxf format and create a file called the output file .dxf. And what this line of code is saying is just like open a file called the output.dxf, and whatever you start executing now on, including the loop, including the library, including everything really, it's gonna be recorded in a Dxf file, right? All the geometry is being recorded. And then we just need to, if we keep this open, we're gonna be recording every frame and it's gonna be repeating the geometry. So we basically at the end of the loop of the draw, we need to close the file, right? So we're gonna say if record equals true again, so the same thing, and you see that I'm gonna just do end raw and also record equals false. So what this is saying is if I enter record mode by pressing R, I open the file, I copy, like create all the geometry into them into that output file, and then I get to the end of the draw, and I basically close the file and also turn that variable into false mode, right? So that won't happen the next frame unless I press R again, right? So if you press R, you will be recording your geometry. This Dxf export, it's really handy, but it does have some problems. Like for instance, it cannot really work with points, right? So I'm gonna get rid of these lines for now. So because if we try to run it with points, we're gonna get an error, right? But it should work fine for lines. And the drop trail, it's actually a series of lines, right? So let's see if we can get these to export. So we're basically doing these lines. They're going up, they're getting somewhere, they're just going all the way around. And maybe I like that form, right? Maybe I like this kind of threaded condition, right? So I'm gonna press R now, and I think that should be done. I mean, we should actually put a message here that says print recording done, right? So just to make sure that the recording has been done. But if we look at in our output, in our folder of the script, right, you should see that we have an output file, and this is a file that it's quite big actually because it has lots of lines. But if you're not sure what I did, I was just like running the script, and at some point I press R, right? So now that nothing kind of appeared, and you probably didn't see me pressing it, but like now you should actually get recording done if you do it again, right? And it's gonna just capture whatever was created in that moment in time, right? So let's open Rhino or any package where you could actually open geometry like this, and I'm gonna file import, and I'm gonna go to my desktop to here, Plethora tutorial and output, and let's see what we got out of that. And you see that we have our geometry. One of the problems that we are getting is that we have this box, so we could just delete that if you want. But also that the PC cam in a way is actually orienting the geometry in a different way. Like what it's actually doing is just like, it's not changing the position of the camera, but it's actually kind of setting the orientation of the geometry, right? I mean, you might think that this is just a bunch of threads, but if you're interested in kind of describing this, the problem as well is that these lines are kind of a series of segments, right? And this is going to be a big problem, especially if you want to do something like piping them or something like that, because you're going to have to start joining them. So as I said, this is a really good way of making a quick export. Let's do a version of that when we don't have the deformation of the camera. So we can try it again. And sorry, this is just the example. So for instance, if we have something like that, let's say that we want to just record that area. So if I double click in PCCam, I'm going to go to the origin location and I can press record here, right? And you see that now recording done has been. And that because we resetted the position of the camera, we should be able now to kind of import this Dxf and in a way have it better aligned to the Rhino space, right? Again, the problem, the big problem that you'll get here if you want to start piping these lines or making geometry out of these lines is that you have to join them, right? Because as I said, they're just a bunch of lines. So if you join them, you just join a few, they're fine. But if you want to join the whole bunch, you might run into kind of lots of trouble, right? If you want to do that, just do it very slowly. I'm probably going to do one tutorial in some point of just how to do different techniques of piping lines, like how to do maybe isosurfaces or different piping in 3D Max or in Rhino or in different softwares to just have different versions of piping. But yeah, this is it for this tutorial, how to create agent trails, how to bring them into Rhino, and how to basically start determining through some vectors, target vectors, where this flocking behavior it's actually going, like from when it's starting and where it's going, and basically kind of start using them as a drawing device, right? So that's it for now. I'll see you guys soon.